This set of notes is about equilibrium and the equilibrium constant. All right, so processes in the universe can be reversible. That can be chemical processes or that can be physical processes. For example, in a physical process, we might be talking about melting and freezing a popsicle, right? I can take a popsicle, I can turn it into popsicle juice, and then I can refreeze it back into a popsicle if I have the shape and the mold, etc., right? It is a reversible process. I can also go ahead and do something with chemical processes. Here's heating a chemical copper hydrate to drive water out, and then adding water back in to turn it blue like we saw in our lab earlier this year. So when we talk about reversible processes, we can often talk about a condition of equilibrium. And equilibrium just simply means that when you have a reversible process, the forward process and the reverse process are happening at equal rates. So in the case of our popsicle, it is if it was at equilibrium, it would be melting at the same rate that it's freezing, which would be kind of weird to think about where that happens, but it happens at the freezing point, or can happen at the freezing point right around that. So again, forward and reverse rates are the same in equilibrium. In terms of chemical equilibrium, it's when the forward and reverse rate of the reversible reaction are equal. So in other words, our forward reaction and our reverse reaction are happening at equal rates. Whole bunch of different reversible reactions down here that can come to equilibrium. So if we think about over here a situation where we have a reversible reaction, and at first the reaction is going in the forward direction, and so you've got what we would call reactants being turned into products. And as that happens more and more, the reaction rate goes down, because we know as the concentration of a reactant goes down, the reaction rate goes down. But that also means that the reverse reaction happening is getting faster and faster as we get more products being made that can turn back into reactants. And eventually you end up with a situation where the rate of the forward reaction and the reverse reaction become equal, and we call that equilibrium. Okay, so here's a very simple reversible system. And so if we think about what happens to it at equilibrium, so the forward reaction or the forward rate is dependent upon the N2O4, and the reverse rate is dependent upon the NO2. Okay, so we can write rate laws for both of those. And what we'll see is that as this system approaches equilibrium, both the forward and reverse reactions are happening. Okay, the rate of the reverse reaction is increasing, the rate of the forward reaction is decreasing, and so eventually you get to a point again where equilibrium is achieved and the rates are equal. So the forward and reverse reactions are proceeding at the same rate at equilibrium, and once equilibrium is achieved, the amount of each reactant and product remains constant. So if I do a different graph that's not rate versus time, but rather concentration versus time, we'll see that the amount of our products increases and increases and increases. The amount of our reactants decreases and decreases and decreases. And then once we are at equilibrium, because the rate of the forward reaction and reverse reaction are the same, the amounts or the concentrations of our reactants and our products stay the same. Okay. Now, important to note that those amounts stay the same, but they are not equal to each other. All right. So the rates get equal, but the amounts do not get equal to each other. They just get constant. Whereas, talk about rates, the rates get both equal and constant. So, what those rates are determine the equilibrium position. And what I mean by equilibrium position is how much, what's the concentration of the reactant versus what's the concentration of the product. That is the equilibrium position. Okay, so the reaction rates determine that. They determine which has a higher concentration or a lower concentration at equilibrium. So if we think about it this way, here's our forward reaction. There's our rate law for the forward reaction, assuming it's an elementary single-step reaction. Here's the reverse reaction. There's the rate law for that. Okay, we know that at equilibrium, forward rate equals reverse rate. So we can write it like this. Okay, so if we rewrite this putting all the constants on one side, the forward rate constant and the reverse rate constant on one side, and all the concentrations on the other side, we can say the forward rate divided by the reverse rate equals NO22 divided by N2O, which is another K. And this K is Keq. It is the equilibrium constant. So this concentration ratio between the reactant and the product at a constant is called the equilibrium constant. So again, this is products over reactants. So some main points that we need to take away just about equilibrium. Equilibrium happens when the rate of the forward reaction is equal to the rate of the reverse reaction. So as many products are being formed per time as products are returning back in time. And those rates are not only equal, but they also are constant at a given set of conditions. The concentrations of reactants and products are constant with time at equilibrium, but not usually equal. So you can have different amounts or different concentrations of the reactants and products. They just don't change once you get to equilibrium, and that's the equilibrium position. And the ratio of those concentrations equals a constant, known as the equilibrium constant. All right, so let's delve into that equilibrium constant a little bit more. The equilibrium constant. First of all, to note, the equilibrium constant is written as Keq. All right, that is the most generic form of the equilibrium constant. It applies to any equilibrium reaction or process. Okay, now we also will sometimes put equilibrium constant in as Kc. Okay, this is the equilibrium constant calculated using concentrations in molarity. So this will be for things that are aqueous. Okay, we can also express the equilibrium constant in terms of Kp. Okay, so this is the equilibrium constant calculated using partial pressures. So that's what we would use for gases. Okay, other equilibrium constants that we might see or that we will see, Ka is an equilibrium constant related to weak acids. Kb is related to weak bases, and Ksp is related to equilibrium related to soluble or things dissolving. Those will be topics or K's equilibriums that we will investigate in future units, not this one. All right, so again, Keq equals the constant of the forward reaction divided by the constant of the reverse reaction, or in other words, the concentration of the products over the concentration of the reactants. In generic form, we refer to that expression as the law of mass action. So considering a generalized reaction, AABB goes to CC plus DD, and it's reversible, where the lower cases are coefficients, the upper cases are species. Okay, so for that particular one, it would say the law of mass action says the equilibrium constant expression can be written as this. So here's our equilibrium constant. It's written as Kc because it's going to be in concentrations. So these A, B, C, and D here would all be aqueous things. And we're going to write that as the concentration of product 1 to the power of the coefficient, the concentration of product 2 to the power of that coefficient, divided by concentration of the reactant 1 to its power coefficient, and concentration of B. Okay, if we have other products and other reactants, of course, we would just add those on. If we only had one reactant or one product, then we would only have one term in there. Okay, but essentially, we've got, again, products over reactants. All right. We mentioned a few slides ago that if we're talking about gases, we're not going to write this as concentrations. We're going to write this in terms of pressures. So if all the chemicals in a reaction are gases in a closed system, we can substitute the partial pressure of each gas for concentration. Thus, equilibrium expression can be written in this way. So the pressure of substance C to the coefficient, pressure of substance D to the coefficient, pressure of substance A to the coefficient, partial pressure of substance B to the coefficient B. Okay, so same kind of expression, except for we're just using pressures. We're not using concentrations. And AP does get kind of picky at this at some point, like especially in a free response. If something is in gas form, they're going to want the equilibrium expression written in terms of pressures. If something is in aqueous form, they're going to want it in terms of concentrations. Now, there is a way to relate pressures and concentrations in terms of the equilibrium constant. So we can relate them using this equation. The pressure equilibrium constant is equal to the concentration equilibrium constant times the gas law times the temperature times delta N, which is the moles of gaseous product minus the moles of gaseous reactant. So in other words, how many moles of gas are different between the product side and the reactant side. Again, product minus reactant. This is derived using PV equals nRT. So if you want to know how we got this equation up here, it is derived from that, and you can look in the book if you're interested in that derivation. It's not important in terms of understanding stuff or in terms of the kinds of questions you're going to be needing to answer, but if you're interested, it is in our book, okay? So essentially this means that if the number of moles of gas do not change from the product to the reactant side, delta N becomes a 0, so the RT section becomes 1, and therefore Kp is going to equal Kc, okay? This expression that relates Kc and Kp is not on our pink sheet, but if you ever needed it for a test or needed it on the AP test, they would give you that relationship. They would give you that relationship. All right, so a few additional things or features or things to note about the law of mass action, or in other words, writing equilibrium constants, is that you'll notice that it came from the balanced equation. Okay, so that means it's independent of mechanism, right? So it doesn't matter what the mechanism is, the Keq or the Kc or the Kp are independent of what the mechanism is. So that's good. Okay, the other thing that we need to understand is that equilibrium can be reached from either direction. So in other words, you can have more reactants to start or more products to start. It's not going to matter. What you're going to end up with is equilibrium being reached. So if you end up with more products, you will shift in whatever, you'll go in whatever direction, forward or reverse, that gets you to equilibrium. So it does not matter. I do not need to start with only reactants, or I do not need to start with only products. I can start with any amount of either, and the reaction will go toward equilibrium. It can be reached from either direction. Okay. Another interesting thing, you'll notice that we talked about Kc in terms of things that were aqueous and Kp in terms of things that were gaseous. So what if they're heterogeneous? What if things are not the same? Let's say they're not all aqueous or they're not all gas. Well, those species would be called heterogeneous, and we would have a heterogeneous equilibrium. In this case, you can see that we start with lead 2 chloride, and we dissolve that into lead ions and 2 chloride ions. That dissolving process is a heterogeneous equilibria because we have different states of matter on both sides of the equilibrium. All right. Both the concentrations of any solids or liquids that we have in a equation are obtained by multiplying the density of the substance by its molar mass. And both of those are constant at constant temperature. All right, so what does that mean? Well, it means that the concentration of liquids and solids are essentially constant. They don't change. And you can sort of think about it this way, right? If I have a chunk of lead chloride, for example, sitting down in the bottom of a beaker, and I ask you what the concentration of it is, you would go, what? That doesn't make any sense. Okay, its concentration of the solid portion is solid, right? It doesn't change because it's not being dissolved in anything. It's not being, the particles aren't moving apart or in the air or anything like that. So basically, particles that are solids and liquids, the concentrations of them are essentially constant. Okay, so this has an implication in our equilibrium constants. it means that the concentrations of solids and liquids do not appear in the equilibrium expression. So if I wanted to write an equilibrium expression for this, I would normally write concentration of Pb2 plus Cl minus squared over the concentration of PbCl2. But we know that that is this is essentially a constant because it's solid. So if I multiply it by that Keq, it's another constant. It gets built into the Keq. So that means that this does not appear in our equilibrium constant. And so we would just say Kc equals the concentration of Pb2 plus times Cl minus squared. Okay, so again, anything that's a solid or a liquid does not appear in an equilibrium expression. All right. So we can go ahead then and we can write equilibrium expressions that give us an equilibrium constant expression. And then if we start going ahead and figuring out what concentrations of chemicals are at equilibrium, then we can figure out get a numerical number for that equilibrium constant. Well, what does that number mean? What does an equilibrium constant number mean? So mathematically, if we think about this, what would cause Kc to be greater than 1? What would cause Kc to be less than 1? Well, hopefully you can see this, right? If I have a number that's on the top that's bigger than the number on the bottom, then I'm going to have a Kc that's greater than 1. So what does this mean? It means the products of NO2, concentration of that is greater than the concentration of N2O4. Okay. Likewise, if it's less than 1, that means my bottom has to be greater and my top has to be smaller. So the concentration of N2O4 would in general be greater than the concentration of NO2. Okay. So there are some exponents involved there, but this is just a generalized statement. So basically, if the equilibrium constant is much, much greater than 1, we say that it's product favored. In other words, there are more products at equilibrium than there are reactants. If K is much less than 1, then we say it's reactant favored. Reactants predominate at equilibrium. All right, so big K's are products favored. Small K's, less than 1, are reactant favored. Okay, or we would say that equilibrium lies to the right or equilibrium lies to the left. Last thing we need to know about equilibrium constants is we can actually manipulate them. This gets useful when we are talking about different reactions or different conditions or different concentrations. It's going to help us go ahead and figure out differences in the equilibrium constant. So first thing that we need to know is that the equilibrium constant in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. And this makes sense, right? So if this is my forward reaction written with reactants and products, we go products over reactants and you get 0.212. But if you want to talk about the reverse reaction, the equilibrium constant for the reverse reaction is the reverse of that. There's your products, there's your reactants, and you get 4.72. So the forward reaction and the reverse reaction, the equilibrium constants are reciprocals of each other. The second thing is an equilibrium constant that has been multiplied by a number, like you might do in Hess's law, is the equilibrium constant raised to a power that is equal to that number. So for example, here is our forward reaction equation. Here's our equilibrium expression for that forward equation. Okay. Let's say that what we're going to do as we do this is we're going to go ahead and we're going to double the coefficients, like we might have to do if we're doing Hess's law and adding different reactions, things like that. Well, if that's the case, then what I've done is I've multiplied everything in here by 2, which basically means then that I've taken this up here and squared it. And that makes sense because essentially what I've done is I've squared the exponents on both the product and the reactant in the equilibrium expression. So again, multiplying the coefficients is an exponent of the equilibrium expression. And last but not least, the equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constant for the individual steps. So, for example, let's say we have this reaction, which again, if I roll it out here, is B plus F goes to D plus G. Okay, let's say we want to find the equilibrium constant for that, but we don't know what it is. However, we do know what the equilibrium constant is for our 2 elementary steps, right? This one here, K1, would equal the concentration of C times D over the concentration of A times B. All right. K2 would equal the concentration of G times A all over the concentration of C times F. Okay, now you'll notice that, though, if I take those 2 equilibrium expressions and I multiply them together, I essentially get our overall reaction in the end, D times G over B times F. Okay, so let's say we didn't know these concentrations down here and they just asked us what's the equilibrium expression here. Well, if we know the equilibrium constant for that and we know the equilibrium constant for that, we can multiply them together and get what should be the equilibrium expression for them together. Okay, so if I'm adding reactions, I'm multiplying equilibrium constants. That concludes these basic notes about equilibrium process and equilibrium constants.